Now that we have seen many properties of the Laplace transform, we turn our attention to the inverse Laplace transform, which is to find a function. So given a function, one has to find a function whose Laplace transform is the given function. Remember that to solve ordinary differential equations, for example, we had to invert the algebraic equation, the solution of the algebraic equation, to find the solution for the differential equation, which I have mentioned before. So finding the inverse Laplace transform is a very important problem, and we will look at various methods to find the inverse Laplace transform of a given function. So in this lecture, we will look at the definition of the inverse Laplace transform and the problem of uniqueness of inverse Laplace transforms. So we ask the question whether given a function in the s variable, whether two functions in the t variable can have a Laplace transform for the given s variable function. So this is answered by the so-called Lurch's theorem, which gives a criteria for uniqueness for the inverse Laplace transform. Then we will look at properties of inverse Laplace transforms. These are the same properties that we learnt about for the Laplace transform, but they are now translated in the language of the inverse Laplace transform. And we will also see in this process the definition of the Heaviside unit step function, which is a very important function which crops up in especially in engineering problems, where when you are modeling an engineering problem such as a mechanical system or an electrical system, and you have to model some kind of force or some other quantity being applied for a finite amount of time, then this function comes in very handy, and this is called the Heaviside unit step function. Then we will look at asymptotic behavior of the inverse Laplace transform. You can also call it the asymptotic behavior of the input function for the Laplace transform. So we will look at two theorems in this regard. One will be the initial value theorem, which relates the initial value of the input function in the t variable near t equal to 0 with the behavior of the Laplace transform of the function s near infinity. So there is a duality in this in these theorems. The initial value problem and the final value problem then tries to relate the final value, which means the limit of the input function as t tends to infinity, with the behavior of the function, of the Laplace transform of the function multiplied by s near t s equal to 0. So these are initial and final value problems, which are also quite helpful in finding solutions of ordinary differential equations, and we will see where these theorems fail with some examples as well. And so we will cover all these topics in this lecture, which introduce us to the basic properties of the inverse Laplace transform. Let's begin with the definition of an inverse Laplace transform. So remember that the Laplace transform was given by a transformation, so which took as input a function ft, and this blue box transforms this function ft, this L transformation transforms this function ft and produces a function f of s. Similarly, the inverse Laplace transform can be viewed as taking the input as fs, and this inverse Laplace transform, when applied to fs, gives a function of the variable t denoted as ft. Now the inverse Laplace transform satisfies this property that the inverse Laplace transform of a Laplace transform is the original function itself. So this is the defining property of the inverse Laplace transform. So in other words, this means that if the Laplace transform of a function ft is equal to fs, then the inverse Laplace transform of fs is the function ft defined for t greater than or equal to 0. So for example, if theta is a real number, then the inverse Laplace transform of theta by s square plus theta square, we know that this is the Laplace transform of sine of theta t. So the inverse Laplace transform of theta over s square plus theta square is equal to sine of theta t for t greater than or equal to 0. Now the question arises that if L inverse of fs equals ft, then is there any other function, then is there any other function gt which is not identically the same as ft, such that the inverse of fs is also equal to gt. So this is the uniqueness problem of the Laplace transform, of the inverse Laplace transform. Inverse Laplace transform. So note here that if I change, if I define a function, I change my function sine theta t to a new function gt, which is defined as sine of theta t for t greater than 0 and let us say half for t equal to 0. So I am just changing the value of the function at just one point. This makes it a piecewise continuous function because it has a discontinuity at t equal to 0. So this is discontinuous at t equal to 0. But when you take the Laplace transform, the integral is not affected by the particular value of the function at an isolated finite point. So the Laplace transform of gt is the same as the Laplace transform of sine of theta t. This is simply because of the property of the Riemann integral and the improper Riemann integral, that if you change the value of the function at just one point, it will not change the value of the integral itself. So these two Laplace transforms will be the same, which means that the inverse Laplace transform of theta over s square plus theta square can also be this function gt. But note that we have this following nice property. We have that the integral from 0 to t, so this is for any t positive, the difference gt minus sine of theta t, gu minus sine theta u du, this is going to be 0 because the difference is only non-trivial at just one point. So these kinds of functions whose integrals from 0 to t is equal to 0, these are called, this is an example of a so-called null function. So let me define what is a null function. Null function. So a function n t such that 0 to t integral nu du equal to 0 for any t positive is called a null function, meaning that the integral must be 0 for any interval that you take from 0 to t. So it's not very difficult to see that the Laplace transform, so let me write it as a theorem, that if nt is a null function, then the Laplace transform of nt is equal to 0. So let's see how this is proved. So now we have the following theorem, which says that if nt is a null function, then the Laplace transform of nt is 0 for any s greater than 0. So we can prove it quite easily. So we write our Laplace transform as nt exponential minus st dt, and by integration by parts we have the following formula. So the first term is exponential minus st integral 0 to t nu du, and the range is from 0 to infinity, plus s 0 to infinity exponential minus st integral 0 to t nu du, and then we have another dt. So we note that these integrals, first note that the derivative, so if I denote this function as ft, then f prime t is nothing but nt. So from this we have the usual integration by parts formula. So therefore we have these integrals of nu du from 0 to t, but all of these are 0. Therefore this is 0 plus s times 0, which is 0, and this is valid for any s greater than 0. Therefore, as a consequence, corollary, we have that if the Laplace transform of a function ft is fs, then the Laplace transform of ft plus nt is also equal to fs for any null function nt. So which means that we can add any null function nt to our original function ft, and we get back the same Laplace transform f of s. So this implies that the inverse Laplace transform of our function fs can be any function of the type ft plus nt, where nt is a null function. So not only we have more than one choices for our inverse Laplace transform, in fact we have infinitely many choices of our inverse Laplace transform, because there are infinitely many null functions. So you can just define any null function using finite values at discrete points. For example, if this is 1, you can put the value 2 here, and at, let's say, at value 5 you can put the value 2.5, and it's 0 otherwise. So our function takes the value 0 if, so this is the interval from 0 to 1, but 1 is not included. At t equal to 1 you get the value 2 at t equal to 1, then you have 0 again, and then at t equal to 5 you have the value 2.5. So, and then you have 0 again. So if you take there is no area under the graph of this function, so all your integrals will be 0, and you can define in the same way infinitely many other functions which still have the integral to be 0. So now the question arises whether these are the only types of functions which can have the Laplace transform fs or not. So this is answered by the following theorem. This is known as Lurch's theorem, which says that if fs is the Laplace transform of some function ft and fs is also the Laplace transform of some other function gt, where ft is not identically equal to gt for t greater than or equal to 0, then ft minus gt is a null function, So this says that up to the addition of null functions, there are no other inverse Laplace transforms. So in particular, if you have if ft and gt are continuous functions with the same Laplace transform, fs, then ft is identically equal to gt, because these two are continuous functions. So ft minus gt will also be a continuous function, and unless it is identically equal to 0, any continuous function will have some area under the curve for some value from 0 to t. So in this sense, the only option for the difference ft minus gt is equal to 0. So we see that if ft and gt are continuous functions, then with the same Laplace transform, then ft must be equal to gt. Now let's look at the properties of the inverse Laplace transform. Now note that since L inverse of fs is ft, where Laplace transform of ft is fs, the properties of the Laplace transform, the inverse Laplace transform, properties of L inverse can be deduced from the properties of L itself, of L. So for example, the first property is linearity. So it says that if fs is the Laplace transform of a function ft defined for s greater than alpha 1, gs is a Laplace transform of a function gt defined for s greater than alpha 2, and alpha, beta are constants, then the function hs defined as alpha times fs plus beta times gs defined for s greater than the maximum of alpha 1 alpha 2, the inverse Laplace transform of hs is nothing but alpha ft plus beta gt. This follows immediately from the linearity property of the Laplace transform. So follows from the linearity of Laplace transform, which means that alpha of Laplace transform of alpha ft plus beta gt is nothing but hs. So you can check the linearity property of the Laplace transform, and this is exactly what we get for the Laplace transform of alpha ft plus beta gt. Now second property is the first shifting property. So for L inverse, so if Fs is the Laplace transform of Ft defined for s greater than alpha, and C is a constant, then if Gs is defined as f of s minus c, where s is greater than alpha plus c, then the L inverse of Gs is equal to exponential Ct Ft for t greater than equal to 0. So is L inverse. So this is just the translation of the first shifting property in terms of the inverse Laplace transform. So for example, the inverse Laplace transform of 2 over s minus 1. So let's try to compute this. So we know that the Laplace transform of e to the power t is equal to 1 over s minus 1. So this is valid for s greater than 1. So the inverse Laplace transform of 2 over s minus 1 is simply by the linearity property 2 times the inverse Laplace transform of s minus 1, which is nothing but 2 times e to the power t. This is defined for t greater than or equal to 0. Now for the second shifting property, so again, if Fs is the Laplace transform of Ft for s greater than alpha, and C is a constant, C is a positive constant, then if Gs is defined as exponential minus Cs multiplied by Fs for s greater than alpha, then the inverse Laplace transform of Gs is equal to the function which is 0 for 0 less than or equal to t less than or equal to c, and it is equal to f of t minus c for t greater than c. So again, this is simply a rewording of the second shifting property. Now we can rewrite it, we can rewrite this function, rewrite this as L inverse of Gs is equal to f of t minus c u of t minus c, where u of t minus c is the function which is 0 for 0 less than or equal to t less than or equal to c, and 1 if t is greater than c. So the graph of the function u t minus c, so let's suppose that this is our point t equal to c, then the graph of the function is 0 up to c, and then it is 1. So this value is t equal to in the y-axis it is 1, and for all values greater than c it is 1. So this is the graph of ut minus c. So the function f of t minus c ut minus c, f of t minus c ut minus c. So let's try to compute this. So if 0 less than or equal to t less than or equal to c, this value is 0 because u of t minus c is 0 for in this region, in the region 0 to c, and here we have implicitly extended the function f by 0, extended by 0 to the negative real axis, because f may not be defined for t less than 0, and when t minus c is less than 0, meaning that 0 less than or equal to t less than or equal to c, then we are just extending it by the value 0. So both values are 0 in this region, 0 less than t less than or equal to c, and so we get a 0 value, and when t is greater than c we get f t minus c, because in this region ut minus c is simply 1. So this function ut minus c has a special name. So ut minus c is called the Heaviside unit step function at t equal to c. This is named after the mathematician Oliver Heaviside, and it's called the unit step function because it takes this step of height 1 at this point t equal to c. So this function is very useful, especially in electrical engineering, and we will see how we can compute the Laplace transform of this function. So let's try to compute the Laplace transform of ut minus c. So supposing that c is greater than 0, so the Laplace transform is simply 0 to infinity ut minus c e to the minus s dt, but from 0 to c this is 0 times e to the minus st, plus from c to infinity this is simply 1 e to the power minus st dt. So this part is 0 and this part is nothing but e to the power minus cs over s, and this is defined for all s greater than 0. So the Laplace transform of the Heaviside unit step function is e to the power minus cs over s for s greater than 0. So equivalently we can write the inverse Laplace transform of e to the power minus cs over s is equal to the unit Heaviside step function for t greater than or equal to 0.